All right, question 5H3 from the second edition of Statistical Rethinking. Make sure you use these code blocks up here to install and load the Rethinking package. Okay, so 5H3. So 5H3 is going to be similar to question 5H2, so you may want to watch that. And in 5H2, what we did is we took a model from earlier in the chapter that we believed had this causal model, built a DAG for it, and then ran counterfactuals. And in that model, in order to run counterfactuals on a DAG like this, we have to explicate each of the relationships among the variables. So we had a model for the M to A relationship and then the A to D relationship. And then we would deduce the M to D relationship by combining these models. 5H3 is similar, but now we have a slightly more complicated model, and you'll see why it's more complicated here in a minute. But we have M affecting both N and K, and then N going on to affect K. So the reason that this is a little bit more difficult than 5H2 is because now we're being asked to manipulate M and see what happens to K in our counterfactual scenarios. But M is affecting K directly, a direct effect, as well as indirectly via N. Okay, and so there's two causal paths to make sense of here, but it won't be that big of a complication. Okay, so first we'll load the data and build a model that we can start to play with. Okay, so here is my standardized data, and this is earlier in the chapter. In fact, I think I just copied and pasted it from the chapter. But I'm standardizing the variables and then just taking the complete cases. So any data that's missing, those rows are omitted. And then I have my models down here. My model, which has two linear models in it. Okay, so the first linear model, M to N, is reflecting this relationship. Okay, and so I have that N is a normal variable, the mean of which is dependent on M. Okay, and so here's the rest of the parameters for the model. Okay, and then we have the next model in which we're modeling K, and K is being affected by both M and N. Okay, so we have K, normal variable with mu K, and mu K is a function of both its intercept and the two explanatory variables M and N. Okay, and so we can go through and we can run this. Okay, and we get our posterior distribution here with the Pressey output. Now, I'm kind of going through this a little bit more quickly than the previous question because the steps are the same and a lot of the code is just copied and pasted with some slight modifications. But we need to pick a variable to manipulate. Okay, and so we're asked to double M. Okay, so we need to set a bunch of different values for M. Okay, and then find the expected values of the different proposed values of M. Okay, and that's what we're doing here with the M function. I am putting M in, and then I want to get estimates for N and K. All right, so when I run this and I look at the structure of it, you see that it creates a list of predictions. So I have 1,000 predictions, well, way more than 1,000, 100,000 predictions. But for every value of M in MSeq, I have 100 values. I get 1,000 predictions. And so I have a matrix for N and a matrix for K here, okay, where every column is a different value of M, and then every row is a different prediction for that value of M. Okay. So now I'm going to plot it. Okay, I'm going to plot the effect of M on N, and then the effect on K of M. Okay, and you can look through the code here. Okay, but I'm just taking the values from my MC variable up here, my counterfactual after changing M object up here. All right. So the left-hand panel is what N is doing as we're changing M, and then we're seeing what K does as we change M. All right. Now notice how wide the credibility intervals are here for the M and K relationship. Way more than the M to N relationship, and this should kind of make sense because if we go up here, there is several paths that are included when I go from m to k, right? I have 1, and then I have this other path that is composed of 2 different processes, a process that whereby m of xn and then n of xk. And each of these processes has its own variability, has error in the measurement, etc. And so, so the more complicated pathway is going to be less certain. Okay, the estimates are going to be less certain. All right. We don't need that code block. Okay, and so now we need to double m, which is the mass of these primates. I believe we're dealing with primates. And so we need to just, I'm going to arbitrarily pick the mean and then and use that as the value that I double. Okay, but we could pick any value really. So so I'm arbitrarily picking the mean, and then I'm going to standardize it, right? Because remember, all of our variables are standardized, right? So this is the code that I use to do that, and when I kick that out, so we see that the average mass of our data, the animals in our data, is about 16.6 kilograms, and then when I standardize not the mean, but twice the mean, it's about 0.7, right? That's the standardized value of twice the mean. Okay. Okay. So finally, I'm going to find the exact values of having doubled the mean here. Okay, so so we see that by that's interesting. Yeah. So we see that by doubling the mass, we have a reduction of about 0.18 standard deviations, right? So here is the plot that you've seen above, and then I've just zeroed in on, so this red line, vertical line, represents doubling the mass in standard units, and then the horizontal line is the prediction for k, right? And so we see that by doubling the mass, we're expected to decrease kilocalories, the kilocalorie concentration, I think, of this primate's milk by about 0.18 standard deviations, or 0.19 standard deviations, or 0.2 is what I said here. Which, when I go to, if I just multiply how much it's changing by what a standard deviation is, then oh, you know what? I don't think that's right. I think I want that to be kilocalorie. Okay, so that's a mistake. It'll be corrected in the Colab, but that should be kilocalorie, not mass. But anyway, I'm not sure what the value will be. Actually, let me pause this and figure it out real quick. Okay, and we're back. And it's less than a calorie reduction, and that was probably apparent given the plot here. Okay, so that is it for this one.